Morning, lads. Bit of a short lesson today. We're going to look at one specific scenario and see how we can apply what we've learned to try and solve the problem. Here we've got a car on a racetrack. The best I could do, I'm afraid. And in this diagram, that car is coming towards you. It's coming out of the paper towards you. And it turns a banked corner of radius 15 meters. That's the radius of the bend. So if I was to show that in the diagram, that would be the 15 meters between that and the center of the bend. In terms of the car's mass, you've got an 1,000 kilogram car, and it's telling you that the maximum frictional force between the car and the track is 20 kilonewtons. I'd like you to pause the video at this point and think about two things for me. First of all, I'd like you to copy this diagram out, and I'd like you to think about what forces are acting on the car. So I'd like you to try and label those forces in a free body diagram, like the diagram we've done before. And I would like you to have a think about why banking the track means the car is less likely to skid. And I would like you to write your answer down for this question. I'd like you to put a bit of thought into that. So if you can pause the video now and do those two things for me. Right, so if we go about doing some labelling of that then, we can start with the weight of this car acting down from the centre of mass. And we can label that arrow mg. At this point, you should recognise this as similar to a previous problem we've seen, the problem of things on inclined planes. That means we can resolve the weight into two components, but we're going to leave that for now and do the rest of the forces before we think about any of that. So we've got the mg acting down. We have the normal reaction force acting at 90 degrees to the surface, R. And then, finally, you've got the frictional force. Got to ask yourself how the frictional force acts here. Well, the frictional force is what's keeping the car from sliding. How would this car want to slide if it was going off the bend? It would want to slide up the track. So you've also got this frictional force acting down the slope, F. Now, those are your forces. Remember, we don't label a centripetal force because it's not actually a force itself. It is just provided, it's something that's provided by other forces. So the second question is explain why banking the track. So rather than this being a flat track, you've got it inclined at an angle. Why this means the car is less likely to skid. To do that, you've got to think about the forces. Now, in terms of this, what causes the car to skid? That must mean that there aren't enough forces towards the centre of the circle, centre of the corner in this case, to provide the centripetal force. So in this case, if this were a flat track, you would just, in fact, it might be easy if I just drew a quick diagram here. If this was a flat track and you had your car coming towards you on the flat track, the only force you would have acting towards the centre of the circle is your friction. In this case, you've got the reaction force as well. So that is your answer there, that it's not only friction that provides the centripetal force, but also a component of the reaction force. So we're going to look a little bit deeper into this scenario now, and the task we're going to complete, I'm going to walk through this with you, is more complicated than you're likely to see in a physics exam, only slightly. A lot of the skills that we practice you will be required to do, but as a question, you're unlikely to be asked it. If you're doing further maths, however, the chances are you will be expected to solve these sorts of problems, so it'll be especially useful for you. And the question is to calculate the maximum speed that the car in this example question can complete the corner on the track. What do we mean by the maximum speed here? Well, we mean the speed that the car can travel at without skidding off the track. So that's the problem, and we're going to start this by the same technique that we looked at with the centripetal problems last lesson. So for that car to stay in circular motion, we know that force in minus force out must equal mv squared over r, which is the same thing as mr, omega squared. Now, at this point, we've got to ask ourselves which one of those formula we need to use. The question's asking us to calculate the maximum speed, which means that this first part of that formula, the first form of that formula, is the correct one to use. So at this stage, remember that's our condition for circular motion, which in this case is the condition for the car to stay on the track. What I'd like you to do now is pause the video and have a think about what forces are acting in on this car and what forces are acting out on this car. So let's have a look at the forces in to begin with. Let's look at this weight to begin with, the mg. Now, the centre of the circle that this car's turning is along this line. The weight here is completely at 90 degrees to that. So that's neither acting in nor out. So we don't need to include the weight in this formula. Let's have a look at this frictional force here. Now, that's definitely acting towards the centre of the circle, but it is not the whole of that force. We've got an issue here that it is actually a component of that force. Now, if we split this force into two components, which we're familiar with doing in 2 dimensions, we can see that component and we can see this component. Only one of those is acting towards the centre of the circle, and that's this top component here. From a little bit of GCSE geometry, we can see that this angle there, because of Z angles, is 15 degrees, the same as the angle of the slope. So to find this component here, we're going to do F, the frictional force, and we know that from the question, F cosine 15 degrees. Are there any other forces acting in? Have a look at this R. Most of this reaction force the biggest component is actually at 90 degrees to this line, telling us about the centre of the circle. But actually there is a small component. So yet again, we resolve into two components. From those rules of geometry, you can see that this angle there is 15 degrees. Which component are we interested in? This one or this one? It's going to be this top one here, because that is the only component which is acting towards the centre of the circle. This line here, it's parallel to this line that's towards the centre of the circle. So we're going to add that. What is it going to be? Is it r cosine or is it r sine? It's the opposite side we're interested in, so it's r sine 15. And that's then going to be subtracted from the force out. So the force out in this case is and not to do with F, not to do with R, not to do with the weight. So there's no force out. That is going to be quite often the case with these questions. The force out is 0, so we can ignore that term, and that's going to be equal to mv squared over R. Let's think about our unknowns now and what we're trying to find. We know F. It's given to us in the question. We're trying to find V. We know the radius R. Big mistake I see people make is getting the R's confused at this stage. One capital R represents the reaction force. Do not get that mixed up with the radius of the curvature of the track, because that is quite a common mistake, especially under the pressure of the exam situation I've seen people make. So we've got the radius of the track. What we don't have is the reaction force. How can we find the reaction force? We can find it by doing a little bit of resolving perpendicular to the slope. We know the car is not accelerating off the track in that case, so we can say that by resolving perpendicular, exactly like we did with the box on the slope questions, we can say the forces going this way, perpendicular to the track, must be equal to the forces going that way. So let's put our angle in here, 15 degrees, and let's resolve perpendicular to the track. So when we resolve perpendicular to the track, what do we see? We see that mg cosine 15, perpendicular component of the weight, must equal r because r is acting completely perpendicular to the track. So we've got r now in terms of m and g. We do know the mass, it's been given us to in the question, so we can substitute that in. I'd like you to now have a pause of the video and see if you can have a go at rearranging that and finding the solution. So let's have a go. We've got f cos 15 degrees plus mg cosine 15 sine 15 equals mv squared over r. We're interested in v squared, so let's rearrange the formula for that. So we have fr cosine 15 plus mgr cos 15 sine 15 equals mv squared, and then we're going to divide that all through by m to get v squared, and then square root it. So I'm going to stop. I'm going to leave that up there so you can see that at that point. I'm going to stop that there. What I would like you to do for this lesson is send me a message on Teams with the numerical answer to that problem. So that's cars on bank tracks. Just to recap, we applied the same condition that we've done for all our circular motion problems, that the force in minus the force out equals mv squared over r. That in this case is the condition for car to remain on track. We then looked at the forces going in and the forces going out. Those two steps are always the first two steps for solving circular motion problems. And we saw that the horizontal component of the friction here, as well as the horizontal component of the reaction force, were the only two forces acting towards the centre of the track. There were no forces acting out, and then we solved the problem. One of the reasons why this is unlikely to come up and not impossible to come up in the physics exam is because it requires a lot of separate steps and brings in this resolving perpendicular to the track as well to find r. So it's a big multi-step problem. They are becoming increasingly more common in the exams, but I've not seen one on this topic. I'm going to set a couple of questions which are similar. Next week, when we're in school again, we're going to be doing simple harmonic motion, the required practical, and I'm hoping to do a few more circular motion problems then. So please make sure you're up to date with your work by then, and I'll see you then.